my pleasure to introduce the second speaker of this morning, Jochen Heinloth from Duisburg-Essen, and he will talk to us on the moment measure conjecture.
Yeah, thank you very much for the introduction. So, and thanks to the organizers for inviting me first to this program and then now to the workshop. Thanks a lot for all the work you put into organizing this wonderful program. I enjoyed it a lot. Okay, so I want to talk about this an old conjecture, which is joint work with Huijing Jiang. And somehow the motivation for this was the question that came up in the talk yesterday somehow. And the question is how to find notions of semi-stability on a moduli problem or an algebraic stack. So that problem has been bothering me for a long time. And for those who have heard a version of this talk before, so the only new thing I have to add in comparison with the previous version is that now it contains semi-stable points. So, but the first part will be almost the same. So the motivation for thinking about this came, well, I mean, first of all, this has been bothering me for a long time. There's kind of a set of educated guesses you can do, and then you find stability conditions, and I don't understand what this means geometrically. And then, together with Jared and Dan, we proved this this criteria. So we found geometric criteria that give us if and only if conditions for an algebraic stack to admit a proper good moduli space. And I thought, this is great, but now how do you actually produce subsets that satisfy these criteria? Okay, so GIT gives one way of doing this, but I was wondering what others could there be, and I only knew one place where a conjectural full answer of a full classification was known, and this is this moment measure conjecture. So this is just one example to try to learn where the geometry might come from. And so the moment measure conjecture looks at a particular example of such a question. So this, this conjecture is, there's this moment measure conjecture. So the conjecture is due to Jedinski-Pirula and Somesim. From the 80s, I think, around 86 maybe. And they looked at the following example. So you take a smooth variety with an action of an algebraic torus of some rank R, where you assume X to be smooth and proper. And well, either you assume it's projective, or a slightly weaker thing is sufficient, so you can assume that there exists a line bundle on X, such that L restricted to orbit closures is ample. So this, I mean, in some applications, this is a nice condition. If you start out with some variety and you have a relative moduli problem, then it's kind of useful to have this weaker notion. You don't need global ampleness. And then they came up with a conjecture. So they had a conjecture for the question. So what are all open substacks inside of the quotient x mod t that admit, so these open subsets, they will all be of the form u mod t itself. So u will be an open, that's the way how they formulated the condition. So which t stable open subsets of x admit a good quotient. Admit a proper, either geometric or good quotient. And they came up with a surprising combinatorial description, a combinatorial classification of all of them. And that's what I would like to explain. And so the guiding principle for all stability conditions I know, and also this classification, is so the for maybe the first thing I should say is that one reason why this is interesting may already be that every toric variety you can think of will arise in this way. And so in particular, there will be many examples of such quotients that are proper but not projective, and so you cannot get them from GIT in the first place. So that's kind of one example, one thing that I found interesting. And the guiding principle is that semi-stability or stability of points is determined locally around points with large stabilizers. Whatever that may mean. But that's my guiding principle, how I think of all stability notions I can think of. These are always obtained by degenerating my objects into objects that have more automorphisms than the generic object. And so that's the guiding principle that also follows this thing. And so the first part of my talk will just be to explain to you what the conjecture is and why it's a reasonable one to have. Okay, so what are the worst points I can think of in my quotient? Well, these are the points where the whole torus fixes. So these will be the torus fixed points. Look at the fixed here. These are the fixed points. That's the whole torus. And now because, I should also, I forgot, should make full disclosure. So in the original conjecture, so X was normal projective. And I can't do normal, but I can weaken the projectivity. I also had the suspicion, but I had the suspicion that they wanted to do this for normal. One reason to put normal was that they wanted to have an inductive proof for the rank of the torus, and then once you take the first quotient, you end up with something that's only normal. But okay, I don't know. So for normal, for normal and not smooth varieties, I simply don't know yet. So now, if you take a smooth variety with a torus action and you look at the fixed points, then the fixed points will be submanifolds, subvarieties that are smooth. So you can actually decompose this. So I will denote the set of connected components. It's just 0 of xt. Yeah, and I will always work over some field. But it's not necessarily complex numbers. Yeah, so these are so these are smooth subvarieties. And now, so these can have changing dimensions, they can be complicated, but if you want to have some concrete, stupid example in mind, let's put up two examples that are completely silly, but it's I mean, I have to draw these things by hand, and so the simplest thing is you could just take the torus and let it act on a product of P1s, or maybe 2 or 3 P1s. Something more interesting. So the torus fixed, and you just add by the standard scaling action on P1. So there the only fixed points will be 0, infinity on the individual components. So you will have 4 fixed points like this. And here you have 6 fixed points. Order them. I will explain why I think of these as a cube in a second. Okay. So now to this setup, they associate a combinatorial object and the T action associate a combinatorial cell complex. As follows. So for every point, you define the cell of X. But as I said, the guiding principle is every semi-stability should be determined around points with large stabilizers. So if I take my point, I can look at those components that intersect the orbit closure of my point non-trivially. So this is just a subset of I. And this is this remark. Okay, and the collection of the cells of the cell complex is just the set of all C inside I, so that this is equal to the cell of some point. And the boundary of a cell is just the cell of the other orbits you find in the orbit closure. So if you look at our examples, I mean, here we have these 4 fixed points. 0, 0, infinity, infinity. Sorry, I messed this up. So if I take a very general point with both coordinates non-zero, non-infinity on both sides, and I close it up, well, the typical cell will just be the diagonal. So I will flow to both 0, and if I go to 0 and upstairs otherwise. But you will find other cells, and these will give you these. So this is the picture of all cells, and in the cube you similarly get all faces of the cubes and some of the diagonals. So grid model of the cube. And so there's this remark. So now I drew these lines, and actually these cells have geometric. This has geometric realizations. And it's actually so in complex analysis, this geometric realization of the cell will be the moment polytope of the orbit closure. But as I'm in algebraist, I want to do this over any field. I have to do an algebraic version of the moment polytope. And this goes as follows. So pick your L, your positive line bundle. So I mean positive on these orbit closures or an Ansel bundle if you like to think about it. And so because this X is smooth or at least normal, you can lift the T action on X to L. And now you can do the following. So you get a map from your connected components into the characters of your torus. By just saying to each fixed point component, you take the character of T given by the action on the fiber at any point of this fixed point components. So I lifted the action to the line bundle. Because these points are all T fixed, the torus will now act on the fiber. This has a character, and because characters are a discrete thing, they don't move along the component, so it doesn't matter which point I choose. And now to a cell, you can take the geometric realization, which is just the convex hull of the characters chi I for I in your cell, and you take this inside this character lattice and you make it into a real vector space. And this was just right, and the fact is the chi I's are the extremal vertices of this realization. So they actually, nobody lies in the interior of these, and the dimension of the cell, so the real dimension of the cell is actually the dimension of the orbit. So, and this, so let me remark why this is the case maybe. So the basic idea for this is very simple. This is just if you take any one parameter subgroup in your torus, and you take your point X, you can just act with this one parameter subgroup on your point. So this will define for you a map from P1 to X. And if this X is not fixed by your subgroup, then this will be a non-constant map. And if you take L and restrict it to your P1, this is positive. Because you assumed, because of this assumption that we had a line bundle that was positive on orbit closures. Right, so on orbit closures it's sampled, so it's positive. But here, you know that the degree of this line bundle, if you think this is a line bundle that is now GM equivariant, and if you look at what this is, so it will just give you the character at 0, or should I say, so the character at 0 paired with lambda minus the character at infinity paired with lambda. So that's the weight of L at 0 times x minus the weight that you find at infinity times x. And this is positive. Does this make sense? Yeah, so I pull back my line bundle, I get the GM equivariant line bundle, I can take the weight at 0 and infinity, and it will turn out to be a number, and the difference of these numbers will give me the degree of the line bundle. And because this is positive, this gives you that these things will be convex hulls. Okay, so that's why this has a geometric realization. And now let's see what happens. So this was the first step. Interesting. And the second fact that I want to remark is that if I have a specialization of points, I think of this as these are sort of so for some discrete valuation ring, well, a small disk, then actually then you can look at this closure, and you, well, I write it down. So then I can take the closure of this family of orbits. So this gives me a family of orbits. In my variety, and I can take the closure, and I can see it what happens when I go to specialize to 0. And then of course here this will contain, so this will contain the orbit of this Tx prime, but it might contain more orbits. So you see this in this picture. If you go locally at the point 0 and infinity in this P1 picture, so this has a neighborhood. That's just the affine line at around 0 times the affine line around infinity. And so if you look there, then the action is on one factor because it's the line at 0. The GM action is contracting, and on the other one it's expanding. And so if you take such this orbit here, this will be a typical orbit, and you can specialize it, say, to this axis. But if you specialize it to the axis, what will you find in the closure? Well, you have to specialize the whole orbit. And so you will not only find this, but you will find these 3 orbits. Yeah. So this happens, that this breaks up. And the fact is, again, and this comes again from a very similar argument that we did essentially this simple computation before, gives you also that the union, if you take the geometric realization of your cell of the point you started with, then this will be a union of the cells of the xi's. Will be, well, let's call this prime. The subdivision of the cell of X. So if you specialize, your cell will break up. So if you are in higher dimension, maybe your cell looks something like this, and if you specialize, it will be cut into pieces. And I don't know how these pieces look like. They may be quite large. Well, only go to a fixed point somewhere. Can be something complicated, so I need some. Sorry, for later purposes I need some properties of this picture. Okay, so this will be a subdivision of the cell. Now, okay, so if I now look back at my problem, I want to find an open subset that has a proper moduli space. So first thing I look for is, well, I want to satisfy this quotient should satisfy the evaluative criterion for properness. So when I take my point x, the generic point of this, it should have a specialization in U. So okay, so all possible specializations are just those orbits. Yeah, so the x prime is one possible specialization, but maybe this was not in U, that's okay, but I have to find one of these. So for all xr's, need to pick at least one of the xi's in U to get properness. Well, that's of course not enough. We also, I mean, this is the existence criterion for the properness. yeah, let me just write down for you what they do. And now if I want to have a geometric quotient, so if I want to have a quotient where the points of the quotient are just the orbits, then I have to pick exactly one. Okay, and so what Bielinski, Virula, and Somese came up with was this notion of a moment measure. Well, there's several versions they wrote down. It's a choice of cells. You don't take the geometric realization, just the combinatorial object. So you pick some cells such that the generic cell is mapped to 1. So by generic cell, I just mean the cell of the generic point, or the cell of some very general point. And plus, the second thing is that if you have some cell and you have some subdivision of it, and let me write this kind of formally. So I take the geometric realization, and then the geometric realization of this thing has the open part and the two closed parts. So I take all these strata, this is this circle, the open part of the corresponding cells. Then should be the sum of the moments of this CIs. So meaning you choose exactly one where this function is non-vanishing, and you call it a geometric if the M of C's only happen to be mapped to 1 only for cells of maximal dimension. So that's the choice they give us for. So you can now play with the. While I raise the board, you can play with the examples of this that are on the board there to pick out your favorite quotients that you can find for these actions. So in the first case, all quotients you find are either point or P1. It's not so many one-dimensional. Rational curves. But you can get these quotients in quite different ways. Should we take the moment to do this? So if you take the geometric realization of the cube that I told you, you will actually get a picture that looks a bit like this. So you take a cube and put it on its so the cells you will find are the upward pointing. So you have the 6 fixed points. And if you look at the weights that you will attach to them, you will attach something like 0, 1, 2, and 3 if you take the standard linearization of the amper bundle of 1, 1, 1. Yeah, so if you take the standard linearization of O of 1, 1, then every 0 gives you 0 maybe, and infinity gives you a weight 1. And so the more infinities you have, the higher the weight that you get. And so the generic cell will be the diagonal of your cube. And now a subdivision will be any path that goes from this lower corner to the top corner. So for example, the subdivision of this generic cell could be this favored path, or you could take a shortcut through some diagonal. Look at these decompositions, and if you want to find nice subsets that are quotients, well, the first subset you might see that has a nice quotient is, well, you just take the affine neighborhood where you take the 0, 0, 0, A1. With the contracting action, you remove 0, you get P2 as a quotient. And this you see if you just take the cells that cut out by these three things. So you just take this cut, but you can take some other cuts like, well, slice the cube into two pieces, sort of vertically. This tells you which paths to take into account, which cells to take into account, and this will give you a quotient that's P1 times P1. And if you take some corners into it, then you will get some contractions or some blowups here, depending on what you do. Nice. And so given M, you define the set UM. So now, I first give you this if M is geometric. Then this is just the set of points such that equals 1, and in general, you take those points where M of C equals to 1 for some cell in the cell of X. So you take the geometric realization and either you take the interior or you'd have some point in the boundary. So in my picture above, you could kind of say, well, I want this line to correspond, this to be a cell that should be semi-stable. Then this definition forces you to also make these things semi-stable. And if you take this point, you want to have attach the value 1 to this single point, then every cell that attaches to it will have to be declared semi-stable as well. And in the quotient, these points will all be contracted to this point, and these points will all be contracted to the quotient of this.
So what are the measures on those cells?
So if I want to declare M of this point to be 1, then this condition says that you have to take all the points that have this cell, but also if you have a point that happens to have this cell, it will also be in U.
It'll also measure 1?
No, it will not have, I mean, there's this problem. The definition is, I can only put 1 once, because I have the sum condition. This tells me I can only put 1 once.
So those will have to be zeros, or no?
They will be 0, but any point that corresponds to that has this cell will be in U. So if you have a point, if you have a point whose cell is this cell, it will be, so the measure of the cell of X will be 0, but X is in UM because the value 1 appears in the boundary of the cell. Yes? That's the rule that's sort of.
So is the measures, are they all zeros or ones? Or
Yes, the measures is just a collection of cells, so you only map to 0 and 1.
Oh, yeah, it's up there, sorry.
Yes. No, yeah, the theorem, which is their conjecture, was that this is actually all that's possible. This was this conjecture. For these varieties, at least. An open subsec U inside X naught T admits a proper good moduli space if and only if U is of the form UMT or some moment measure M, the quotient is geometric so also known as coarse moduli space. If and only if the M is geometric. So in the sex project, the geometric quotients are called coarse moduli spaces. And so geometric quotient just means that the points of the quotient are the orbits that appear here. Any questions on the statement? Yes.
Do we see which one of these actually gets some sort of GIT? Which one of these opens in this example?
Yeah, so
in this example,
in these yes. So in the okay. In these examples, they all come from GIT, but it's just because I didn't dare to make this two-dimensional cell complex. But here, sort of, there's one way to do GIT, and this is to use your line bundle L as a linearization, and then sort of shift the linearization so you can just take any point on the line and take the cells that are pre-images of this. This will give you GIT quotients with respect to the possible linearizations of your line bundle. Now, if you change the line bundle, the geometry of this cube will change. So in particular, these edges can change sides, and so you will get other quotients as cuts. Yeah, so the fact that I put 1, 1, 1 here makes these three corners on the same level. And if you put different ones, then they rise in different levels, and they can then you get other. So the topology of this quotient doesn't depend, but GIT sort of puts a metric on this. Yes?
Why is the group always the colors? Where do you use them?
For at many places. So for the time being, the group is the torus. So for example, this well-behavedness of fixed points is good. If I have a reductive group acting on a projective variety, it can act without any fixed points. Like P1, you have the GL2 action, there's no fixed point. So if you want to think about reductive groups, well, you ask again at the end of the lecture. Yes? Yeah. So it's a legitimate question, but it's sort of for now it's everywhere. But it's not entirely unexpected for the moment, because if you happen to know these valuative criteria that we gave for this existence of good moduli spaces, then only torus only commutative, only GM subgroups appeared. So it's not so absurd that the tori will be the ones that declare whether a point is semi-stable or not. Okay, so right. So let me yeah. Just disappeared. So I should put the first remark maybe. So then it was known the admits, all UM admit proper good moduli spaces. Yeah, so maybe I should try to answer your question again. I mean, in this cell complex, a line bundle gives me a way to project all cells to a plane. And then the GIT stability conditions will always pick a point in this plane and say the points that are semi-stable are those whose cell contains this given point. And sort of different line bundle will project your geometric object in different ways. But you can easily imagine that you can find cell complexes where it's impossible to project a given choice of cells such that they all intersect. And there are various, even for two-dimensional tori, there's simple examples in these old articles. So they knew that these obtain good moduli spaces, and first when I first started to think about this conjecture, I was kind of, I thought now we have these fancy criteria, this should help to prove this conjecture. And then if you read the proof, with having these criteria at hand, then you think, well, actually, sort of, they knew these criteria for these quotients. They actually checked as completeness, and so the argument is not so hard. So the existence of specializations is sort of by construction. Yeah, so we just enforced this condition that whenever you have a specialization of cells and you had the generic point mapping to your semi-stable part, you will get this, the special fiber will be a union of cells, and your moment measure will take the value 1 also on one of these. And this will be the specialization you find in U. So existence of the evaluative criteria for properness is sort of by construction. Satisfies evaluative criterion existence. Of part of evaluative criterion for properness. Now, for separativeness, well, in our article, in our language, we would call this as completeness. And maybe because someone asked me about it, maybe let's recall what this is briefly and say why it holds here. So the idea is the following. So what's the problem with possible not unique specialization? Suppose you have a map. You have two So suppose you have two families over a disk, and they agree on the outside of the puncture. You have two specializations. Then, as completeness says, so this thing you can put into the local model of this quotient of the A2 with the anti-diagonal action. So this is a local version of this thing. So if you take the quotient here, you will get two disks that are glued outside the origin. And so the S completeness says you can fill this in uniquely. So this is sort of what you want for good quotients. You want that well, you might have several specializations, but then there's only one closed orbit that meets them all. And this is what this criterion gives you. And how do you prove it here? Well, you would try to extend this here. So maybe you cannot, but because X is proper, this means that we can extend after blowing up at origin sufficiently many times. So this is a codimension 2 extension problem. I can always solve it in a projective variety. So then I will not get an extension here, but I will have glued in a bunch of projective lines. But now I know that here on the lower thing and on the upper thing, I am both in, if I assume that it was both in U, then this will be both cells in UM. But here I know that, again, by this positivity, the sequence of degree, this line bundle I had was positive on these chains. So I will find inside my complex, I would find a P1 inside of this UM. Well, that's not possible, because inside of a star, something that comes from cells like this, it's not possible to have a P1. So to blow up, not possible, not necessary, because UM mod G does not contain P1 mod GM. Yeah, like this positivity thing. So that's essentially the argument that they also had in their article. And we have also theta completeness, but that's the same argument works. And if I understand, David will tell you that we don't need to check it anyway in this situation. Okay, good, so 10 minutes. So then the 10 minutes are to tell you a little bit why. So the real question they had was how to get a moment measure from U. And this is a bit surprising because the set of all points X such that the cell of X is equal to some given cell, this can be disconnected. And the second trouble I have is that not all cell decompositions arise from this procedure of specializing. So it's quite easy to write down examples of complexes that have fixed point strata, for example, like this. Where you have these are sort of I don't know, 3, 4, where you have specializations in this way, and then you will find that you can, your generic cell will be this interval. And you will find subdivisions like this. But I'm running out of maybe not so many colors. You will get a subdivision like this. That of your interval that doesn't correspond to an orbit closure. And so somehow it's quite kind of, this conjecture at first sight looks kind of strange because, well, when we came up with this procedure, why should we have to make the same choices for different components? And why do these things put any conditions on my cells at all? It didn't show up. So that was a bit of a surprise, but they made the conjecture because they could prove it for rank 1 and rank 2 over the complex numbers. And the idea was kind of simple-minded to prove this. Yeah, maybe.
Sorry,
Yes?
you assume that the main theorem, do you assume that everything is of 10 to 0 or?
No. No, the point is that there's no need to. I mean, because torus, I mean, the action of a split torus is, I don't know many results that would hold in characteristic 0 but not in characteristic P. So these are all okay there. And because we are taking torus quotients, the quotients will automatically be a good quotient because the stabilizers will all be linearly reductive because they're subgroups of torus. Yes. So the proof idea is kind of so 6 minutes. So originally I just had this result for geometric quotients, and the idea was kind of simple. So in this situation, I look at cohomology. So I can just get a restriction map to cohomology, and if I have a geometric quotient, then this cohomology with rational coefficients, say, I just put the L because somebody asked about positive characteristics. On rational cohomology, these are isomorphic. And in particular, if I take the top dimensional class here, I get here a one-dimensional vector space. Because this is proper. So here I get a one-dimensional vector space. Now, in this top dimension, so this is here it wouldn't be fair to write top, so write twice the dimension of x minus dimension of t. So by the way, I always assume that the generic point has no stabilizer. Otherwise, I just divide out and take my new torus. So here, in this thing, the interesting thing is that for every point in my space, I get the cycle class of the orbit closure divided by t. And you have to multiply it by the order of the stabilizer of x. This is a cycle class, and this cycle class will map to 0 here, to something non-zero here, if and only if this x is in U. Simply because, I mean, if I have this thing, then every closed point will give me a generator for the top cohomology. So if I have something that lies in U, this class will not vanish here. And if it does not lie in U, well, then this cycle class is the cycle class of the empty subscheme, so it's certainly 0. Okay, what does this buy me? I would like to compute, so whether or not the class is in U depends only on its cycle class. And this cycle class, I can apply localization to the cohomology of these Fi divided by T, which turns out to be spectral sequence degenerates. It's just the cohomology of here. And I can compute what this localization is here. And do explicit computation of the image. And what you find is actually you get the cycle class of the point tensor something in, let's call it EX. And this EX turns out to only depend on the cell of X. And yeah, I have 2 minutes, so I don't tell you how I do this, but it's not a particularly hard computation because you know by Bielinski-Birula decomposition, so if you can go to this fixed point, you can go by a one-dimensional, by a one-parameter subgroup, so you will have an attracting subset there. The normal bundle to it will have, and sort of the characters in this bundle and in the normal bundle will be completely determined by the cell. And what you get here only depends on what characters appear in Fi plus and what in Fi minus. And then you have to do some work and compute this. And then this completes the proof somehow. Because then sort of the question whether or not a class is in U depends only whether the cycle class is 0, and this depends only in the cell of this. And from this you can compute that it actually gives you a moment measure. Now, in the last 1 minute 20, so if I do good quotients, what's still true is that if you divide by the So the problem with these stabilizers is always that the kind of what behaves well in families is not the image of the cycle class map, but the Tx. And so this might, so the map from T to Tx might be a finite cover, and in this case, yeah, you should multiply the cycle class by this degree of the covering in order to have good behavior in families. And so if you have a point that has a positive dimensional stabilizer, very similar things happen. You just have to take the quotient by the maximal torus that you find inside. So this is the connected component, and we take the reduced subscheme of it, and this reduced only matters in characteristic P. And otherwise it's automatic. And then, well, this class doesn't live in here. It lives in some other degree. And this is no longer isomorphic here. But, well, at least it lives in this degree, and this fact is still true. So the class, so both claims are still true. You do a local computation. This cycle class still only depends on the cell, and it is non-zero in here if and only if the point was in U. It's a computation. Okay, I have minus 34 seconds. Okay, so the key point is to show that this satisfies this this condition. And yeah, there's no time. Sorry.
Thank you. Question?
Just to clarify, these composite one like don't have these schemes, right?
They are always schemes because I'm dividing by torus.
Okay.
So they are always you see to construct these, you can always take an affine cover of this with a torus action, and these affine quotients are always schemes. And then so the point is that if you have a torus action, you can actually find affine subschemes on which the torus acts. For a reductive group, you only get an état map.
So my question would have then been whether you can read off like properties of this good moduli sort of from the moment measure, but then my question should be maybe can you read off something like projectivity or something from there?
Yes. Yes. As I said, sort of in the simple examples, it's the answer is if I know the Picard group of X, then the answer is yes, and probably in general. So sort of when it's projective, then it rises from GIT, and I'm not sure that I can tell you. Yeah. So yes. So there's a complicated answer. There's no real. I don't know of a very simple answer that would. I mean, that just looks at this moment complex. So I need this moment complex plus the Picard group of X and how it puts these geometric structure on the moment complex, and that's maybe not so satisfactory. But if you are on Pn or products of P1s, then the answer is yes. Yes.
Maybe you mentioned this. So if I ask for separated, not necessarily proper modulate spaces.
Yes.
And is there a similar story?
Probably. Yes. No, I'm halfway joking. So there are some classical examples where you have kind of maximal subsets of these things that admit separated quotients that are not proper. And for these, I haven't really. I would love to have this answer, but I do not have it yet. And this really uses properness. I use the top cohomology. And it's a good question.
Can you comment if there's any perspective of using this for in birational geometry to go beyond the projective setting? In particular, if you have more in dream space, and you sort of use this circle of ideas to obtain birational spaces that are proper but not projective.
It's something I would love to do, but yeah, I don't know. That's the fair answer. But of course, I mean, this is sort of in some sense, it's a test case for me to try to come up with sort of to make this guiding principle precise. And in this case, if I ask for proper moduli space, then these things are determined by cohomological invariants that do not need to come from the second cohomology group, like Picard's, like Chern classes of line bundles. They can arise from different cohomological degree. And yes, I would love to look at some of these examples, but I have not.
So suppose you have a reductive group action and you choose a maximal torus and you do exactly the same combinatorics with weights of the torus, but replacing the closure of the torus orbit with the closure of the reductive group orbit. So you have this closure, you look at the fixed point of the torus.
That's the first thing I wanted to try, and I think it's, if I read the papers of EMGW05 and okay, is she a teacher? I guess so, yes. She has even more Polish letters than me. Sorry, it's difficult to pronounce, and I didn't ever have the chance to ask her how to pronounce. Yes, so yes, so I once asked her. Yeah, okay. Anyway, and they have a clever solution, and they say so. They do this for projective spaces, and I think this is quite general. So I think in general, what I would love to do for quotients by reductive group is to replace these things by some theta strata. And in this direction, I think it's what they do is, well, just consider the quotient of x by t. And if you find a good quotient there, then I can produce for you a good quotient for g. And the trick is, That looks surprising, right? But I think there's a trick that does this, and you just artificially sort of saturate the complement. And if you think long enough, then the saturation is not as bad as you think at the moment, at the first place, and I think this should work. But I haven't spelled it out, so I think this works, and it would have it has the nice advantage that kind of, I mean, as I said in these examples, I mean, if I want to look at points that stabilize as a reductive group, then I will have these flag varieties appearing as closed orbits. And it might be a bit complicated to compute. I mean, the cohomology classes, and these are much easier to compute. And I think this makes sense.
Okay, more questions? If not, we thank Jochen